Today's video is going to be on the scientific notation way of seeing numbers. And when we talk about the scientific notation, it is usually a number like 4.5 times a base 10 number in exponential notation. And with the scientific notation, it gives us the possibility of working with some very large numbers or very small numbers that are in their standard look that a calculator can't even work with because they're so large or so small, that we can put it into this scientific notation so we can work with it and calculate out numbers. We'll demonstrate that in another video of how that works. What we're going to talk about in this video is how we convert from scientific notation to standard notation, which means normal look. And then we'll also demonstrate from the normal or standard notation how to convert that into scientific notation. So the first example I have here is 4.5 times 10 to the third. So if we're looking at this particular number, there's a pattern to see. And the exponent that you see with the base 10 number tells me that I am going to move the decimal, because the decimal system is created from base 10 numbers, that I can move this decimal that's in this number 3 places. Now, which way do I go depends on if this exponent is positive or negative. And because it's positive on the number line, you would always head right from 0 for positive numbers. So that's my mnemonic device to remember which way I have to go with this decimal on 4.5. I'm going to head to the right 3 places. So my work that I would have, I'm going to head right because of the positive 3, and how many places I'm going to move it 3 places. Why I do the loops is because those are place values that need to be filled in with zeros. So when I do that, I have moved now my decimal 3 places from the original spot of 4.5. It went 1, 2, 3. So my answer then is 4.5 times 10 to the third is the standard look of 4,500. And that would be the standard or normal look of this scientific notation look. So the same thing works if I am looking at numbers that have a negative exponent. So to get rid of those numbers so we don't get confused, let's look at this number. 4.5 times 10 to the negative 2. And when we have negative exponents on a base 10 number, or any base number, so it can be any number from 1 to infinity, if it has a negative exponent, that signals me that I have a number less than 1. And in this case with base 10 numbers, there's a pattern also to go by this exponent. So if it's a negative exponent, negative numbers on the number line are left of the 0. So that's the same thing. I'm going to head left with this decimal of 4.5. Again, we're still using that number times 10 to the negative 2. So because of the negative exponent, that means this decimal is headed left. And how many places it goes is again the value of that exponent. So I am going to head 2 places to the left. So if I put my work here at 4.5, there's my decimal, and if I'm going to move it 2 places to the left, my loop would say, oh, I've got a space to fill in with a 0. So my answer then becomes 0.045 as the standard look, standard form look of that number, normal look of this scientific notation number. 4.5 times 10 to the negative 2 is really, in standard normal look, 45 thousandths. So if we want to look at doing the opposite, now I have the standard normal looking number, and these numbers are small numbers and large numbers. But I can think of it the same way. I don't have enough space to write, or I eventually, that we're going to talk about in another video, I want to do a calculation with this big number or this small number, and scientific notation will help us get to that answer a lot easier. So I have 27 billion up here, written, and I want to change that to scientific notation. Now I have to think any positive exponent is always going to be more than 1. Any negative exponent of a base 10 number is always going to be less than 1. This number is less than 1. You don't see any whole numbers out here. This one is definitely bigger than 1, so we're going to have a positive exponent when we're done. So what scientific notation says is that you should only have one single digit as a whole number. Now if something comes out that you don't have that whole number and you have your decimal in some other place, probably I'm still going to say it's correct as long as you have the exponent correct of the base 10 number. But try to always do that. And so if I see this 2 and a 7, if I make one single whole number, where would my decimal go? It would go between the 2 and the 7. And then I would have 2.7 as the number I'm going to multiply by a base 10 number. And what is that position that I go to get this to this? I think about, well, where's the decimal in this big number? Every whole number has a decimal right after the ones place. So there's that decimal, and here's the decimal that I want. So how many places is from here to here? Well, if I think about, okay, there's that decimal right there, and so if I count those place values, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that's how many places I would have to move the decimal from this position to get to this position, because this is my final answer, you might say, as a standard number. This is what I start with. So if I move this decimal 10 places, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so my answer in scientific notation will be 2.7 times 10 to the 10th, and that's scientific notation of 27 billion. Now, notice positive exponent, yep, number is greater than 1. So you'll always have numbers greater than 1, positive exponents. And so if I just simply show where those decimals, where you start or end up with, what's the place values to get there, that's going to be your exponent value. So let's take this small number. What do we have? We're going to know that, again, find one whole digit in this number, and again I have the 2 and the 7 here, so I can say I'm going to put my decimal at 2.7 times 10, some power of 10. Well, it's less than 1. There is no whole number, so that's less than 1. I know I have a negative exponent. It's going to be that way for an answer. So now again, where's that decimal at? Oh, it's right there, same place. So how many places between the original decimal to where I want to put it? 1, 2, 3, 4. So my answer would be 2.7 times 10 to the negative 4 would get me here to here. And thinking backwards from the last slide that I had up here, counting how many places, oh, I'm going to go left 4 places. 1, 2, 3, 4, because negative 4 says head left, go 4 places. And that would get me to this, get rid of that decimal there, that would get me this answer, 0.00027, if I went 4 places to the left with the pattern that I have with the scientific notation. This one would say, okay, I'm going to go 10 places to the right, so as I do this, I'm going to start looping and go 10 places from here, which I'm going to get rid of that decimal again because that doesn't make sense. So, but from here to here is 10 places to the right with this decimal, and I would end up with this large standard form looking number of 27 billion. So if you are struggling with scientific notation, if you are a person in that situation, please watch this video several times. Hopefully that helps you understand the pattern you need to take, whether you're converting from a standard notation or you're going from scientific notation to standard.